What El Niño will do to Earth in 2024. El Niño is a climate pattern that occurs when ocean temperatures in the equatorial Pacific rise above average. This leads to changes in global weather patterns that can have major impacts around the world. With a moderate to strong El Niño predicted for 2024, scientists are anticipating significant effects on the climate this year. What is El Niño? El Niño is a natural climate pattern that occurs when equatorial Pacific Ocean temperatures rise above average, typically by 0.5 degrees Celsius or more. This warm phase combines with the Southern Oscillation, a seesaw pattern of surface air pressure between the eastern and western tropical Pacific, to create the El Niño Southern Oscillation, or ENSO cycle. During El Niño, easterly trade winds weaken along the equator. This allows the warm pool of ocean water that is typically situated in the western tropical Pacific to migrate eastward toward South America. As this warm water spreads, it suppresses the normal upwelling of cool, nutrient-rich water along the west coast of South America. The result is a basin-wide warming event. El Niño generally recurs every 2 to 7 years, typically developing during the northern hemisphere spring and reaching peak strength during late fall and early winter before fading the following spring. Each event differs in strength, timing, and impacts. Major El Niño episodes occur about every 15 to 20 years on average, while the most powerful events happen approximately twice a century. How does El Niño form? Several factors contribute to the development of El Niño events. Weakened trade winds. Under normal conditions, strong easterly trade winds blow from east to west across the tropical Pacific, piling up warm surface water in the western Pacific. During El Niño, those trade winds weaken or even reverse direction, allowing that warm water to flow back eastward. Ocean-atmosphere coupling. Interactions between the ocean and atmosphere, known as coupled ocean-atmosphere feedbacks, reinforce and amplify the changes. For example, weaker trade winds reduce evaporation, which leads to increased sea surface temperatures, which in turn weaken the winds further. The Southern Oscillation. Changes in surface air pressure between the eastern and western Pacific, known as the Southern Oscillation, modulate trade wind strength. The negative or reverse phase aligns with El Niño conditions. Thermocline variations. The sloping boundary between warmer surface water and colder deep water, called the thermocline, flattens out during El Niño, reducing upwelling of cold water. Kelvin waves. Massive subsurface Kelvin waves transfer heat by traveling east across the Pacific to deepen the thermocline in the eastern Pacific and initiate ocean-atmosphere coupling. Interdecadal cycles, slow-moving cycles of ocean and atmosphere variability occurring over decades, further modulate ENSO patterns. Factors like wind bursts, atmospheric disturbances, or even the timing of earlier El Niño events can serve as triggers that help initiate this complex chain of oceanic and atmospheric feedbacks. While the exact cause is difficult to pinpoint, the end result is a large-scale redistribution of heat and energy within the tropical Pacific, leading to dramatic changes in global weather. Typical global impacts of El Niño. By disrupting normal ocean temperatures and circulation patterns across the Pacific, El Niño alters atmospheric moisture content and jet stream configurations, resulting in climate anomalies around the globe. Typical effects include increased precipitation across the central eastern tropical Pacific and parts of North and South America. Drier conditions over Indonesia, Australia, the Philippines, and other islands in the western tropical Pacific. Shift in the jet stream over North America, leading to a warmer, wetter winter in the southern U.S. and a drier, cooler winter across the north. Fewer hurricanes in the Atlantic Basin, but increased storm potential in the eastern Pacific. Weakened monsoons and reduced rainfall over India, Southeast Asia, and northern Australia. Coral bleaching due to warmer ocean waters in the central and eastern tropical Pacific. Changes in marine ecosystems and fisheries distributions. However, each El Niño event is unique, with its own distinct set of climatic influences. The severity of effects depends on the strength of the temperature anomalies and other interacting climate drivers during any given period. Forecasting the 2024 El Niño. Based on current climate models and conditions in the Pacific Ocean, forecasters are predicting that a moderate or potentially strong El Niño will develop in 2024. Several factors point to increased odds of an El Niño year. Observed oceanic Kelvin waves. Large subsurface Kelvin waves which transfer eastward heat were observed in 2022 and early 2023, helping establish warm surface water conditions in the central eastern Pacific, characteristic of pre-El Niño conditions. Equatorial Pacific Ocean temperatures. Sea surface temperatures have been above average since mid-2022, exceeding El Niño thresholds at times. Ocean heat content is also rising, providing more fuel for El Niño development. Eased trade winds and low pressure. Trade winds have remained weaker than average across the basin. The Southern Oscillation Index has trended negative, indicating a likely El Niño. Climate cycles. Climate indicators like the Pacific Decadal Oscillation, PDO, and Interdecadal Pacific Oscillation, IPO, are in phases that favor El Niño formation. Model forecasts. Most computer forecast models predict an El Niño by summer 2024, potentially strengthening into fall and early winter. However, forecasts made a year in advance can be uncertain. The exact timing, duration, and intensity of the 2024 El Niño is still difficult to pin down conclusively, as the event may shape up differently than models indicate. Forecasters will be monitoring conditions closely in the coming months. The severity of these and other impacts will depend on the eventual peak strength and duration of the 2024 El Niño, as well as other climate factors. While the general effects are anticipated based on historical El Niño patterns, all locations should closely monitor forecasts throughout the year. Early preparation can help mitigate damage from related weather extremes. Advancements in El Niño prediction. El Niño prediction has steadily improved in recent decades thanks to enhanced computer modeling, satellite monitoring, and a better understanding of ocean-atmosphere interactions. However, challenges remain. Complex climate processes. ENSO prediction is limited by the inherent chaos of the coupled ocean-atmosphere system. Small errors can grow over time. Model uncertainties. No two prediction models are identical. Forecast variations among different models can muddy certainty. Remote sensing limitations. Satellite sensors cannot directly measure subsurface ocean temperatures or thermocline depth, key El Niño precursors. Data assimilation. Weaving increasing amounts of real-world observations into models is an ongoing challenge. To boost forecast accuracy, researchers are developing higher-resolution coupled climate models, improved mathematical techniques, expanded observation networks like deep ocean buoys, and better methods for reconciling model differences. While El Niño prediction will always involve some degree of uncertainty, these efforts help narrow the cone of potential outcomes. Even modest forecast improvements can significantly aid preparedness efforts. Preparing for El Niño in 2024. From governments to farmers, water managers to disaster relief organizations, stakeholders worldwide should prepare for El Niño's potential impacts in 2024. Improving forecast communication. Tailored forecasts should reach vulnerable sectors well in advance to maximize lead time for preparedness. Bolstering adaptive capacities. Investing in resilient infrastructure, management strategies, and support systems helps communities endure extremes. Enacting preventative measures, early drought declarations, planting drought-tolerant crops, staged water releases from dams can mitigate El Niño's effects. Pre-positioning relief resources. Strategic pre-deployment of medical supplies, water treatment equipment, and other critical assets avoids logistics delays. Monitoring evolving conditions. As the event unfolds, continual observation and recalibration of forecasts ensures response efforts remain targeted and effective. Managing natural resources, fish quotas, irrigation allotments, and habitat protections can be adjusted to ease ecosystem impacts and conflicts over scarce resources. Coordinating transboundary cooperation, open communication, and collaborative planning across borders enhances regional response coordination. Boosting early warning systems, expanding observation networks, and warning dissemination helps protect lives and property. With vigilance and preparation, societies can build resilience against El Niño's stormy side while harnessing the opportunities it may create in some regions. Careful foresight in 2024 may pay dividends when the next El Niño cycle eventually swings to La Niña, bringing its own set of climate anomalies. The intertwined dance of El Niño and La Niña. El Niño and La Niña comprise opposite phases of the coupled ocean-atmosphere system that spans the tropical Pacific. Together, they make up the El Niño/Southern Oscillation (ENSO) cycle, an intricate give-and-take dance between the sea and the atmosphere. During La Niña, easterly trade winds intensify, ocean temperatures in the eastern equatorial Pacific cool, and the thermocline rises as cold water upwells from below. The effects reverse those of El Niño, reinforcing altered weather patterns. Shifts between warm El Niño, cool La Niña, and neutral conditions create an irregular oscillation. While El Niño dominates with more frequent and intense events, even a weak La Niña can bring significant climate impacts, as evidenced by the moderate 2010-12 and late 2020-early 2022 La Niñas. Research reveals this ENSO dance has influenced Earth's intricate climate system for at least 130,000 years, and perhaps much longer. Embedded in the ENSO cycle are clues to past climate shifts like Ice Age cycles and regimes like the Little Ice Age, interactions scientists are still striving to unravel. While ENSO's rhythms defy predictable cycles, its effects permeate multiple spheres of life on our planet. By altering rainfall regimes over more than half the globe, ENSO impacts agriculture, ecosystems, tropical storms, wildfire potential, and economies worldwide. Yet ENSO's dance holds opportunity as well as challenge. Through careful monitoring and preparedness, societies can move proactively to mitigate hazards and maximize favorable conditions during ENSO's phase shifts. While ENSO's varied moods will continue to challenge prediction, sustained research is unlocking its secrets and improving our readiness to partner in the dance. Unraveling the mysteries of deep time, El Niño behavior. The rich history embedded in Earth's oceans, ice sheets, corals, tree rings, cave formations, and sediments is beginning to reveal El Niño variations on timescales spanning millennia to millions of years. What can deep time patterns teach us about El Niño's past and future dance? 100,000 years, Ice Age cycles. Glacial cycles over the past million years exhibit strong links with ENSO variations on millennial timescales. Carbon dioxide changes tied to El Niño activity may have helped drive glacial-interglacial transitions. 10,000 years, Holocene variability. Sediment records show the frequency and intensity of El Niño events has fluctuated throughout the stable climate regime of the Holocene epoch. Large El Niños occurred roughly every 1,000 to 2,000 years. 1,000 years, medieval shifts. Evidence suggests the medieval climate anomaly period from 900 to 1300 A saw increased El Niño frequency. La Niñas dominated the cooler Little Ice Age which followed. 500 years, Pacific regime shifts. The Pacific may transition between periods of ramped-up El Niño activity and suppressed El Niños on centennial scales. Industrialization may have coincided with an El Niño-dominant regime. 130 years, ENSO stability. Modern records indicate ENSO cycles have remained robust over recent centuries. but human forcing may now be overriding natural variability. While gaps exist in the records, these insights provide context on ENSO variations beyond the relatively stable patterns observed since 1900. How much future climate change may alter El Niño's deep time dance remains uncertain, but peering into its past is expanding the horizons of ENSO prediction. Climate change and the future of El Niño. The atmospheric and oceanic circulation patterns that shape El Niño have existed for thousands to millions of years, but human-caused climate change is now disrupting Earth's energy balance. With increasing evidence, it is already altering El Niño cycles in ways that will likely intensify into the future. Observed changes. More extreme El Niño and La Niña events since the late 20th century, as measured by temperature anomalies and impacts. Shifting El Niño teleconnections, the climate effects associated with the pattern. Lengthening El Niño duration and greater frequency of Central Pacific El Niños. Possible future changes. Increased intensity of extreme El Niño events. More frequent Central Pacific El Niños. Shorter intervals between El Niño events. Still possible but reduced likelihood of mega El Niños. Weaker La Niña events on average but more year-to-year variability. However, uncertainties exist regarding ENSO's future behavior and global impacts under continued climate forcing. Accurately modeling how the complex system will respond is an ongoing challenge. Interactions between human forcing and natural climate cycles further cloud projections. Background conditions may modulate how ENSO responds to greenhouse gas forcing over time. Continued research and model development is critical to constrain projections of changes to this influential climate phenomenon. Regardless of uncertainties, it is increasingly clear Earth has entered uncharted territory regarding El Niño dynamics. Careful monitoring and adaptive management will be essential to navigate its altered dance. The human influence on El Niño. While El Niño arises from natural climate processes, growing evidence suggests human activities may be putting a discernible fingerprint on ENSO cycles. Greenhouse gases. By warming the atmosphere and oceans, increased greenhouse gases from fossil fuel burning and deforestation may be intensifying El Niño impacts. Aerosols. Emissions of light-reflecting aerosols like sulfates and smoke can regionally alter sea surface temperatures and atmospheric circulation over the Pacific to modulate ENSO. Land use change, deforestation, agriculture, and other land use changes modify moisture fluxes from land to sea, which can affect El Niño development. Resource exploitation. The depletion of groundwater and oil in regions like Indonesia may subtly alter the distribution of mass enough to influence El Niño cycles over time. Model simulations indicate observed El Niño changes to date cannot be explained without including human climate forcing. However, uncertainties remain regarding the exact mechanisms and degree of human influence. Disentangling natural ENSO variability from human factors is an ongoing challenge, but an essential one. Clarifying the scale of human impacts is key for projecting how El Niño may respond to our still evolving emissions and land use choices in the future. The journey ahead for El Niño science. While El Niño research has yielded profound insights, much remains unknown about this complex phenomenon at the heart of Earth's climate system. Key frontiers include improving predictions, building higher resolution coupled models, enhanced monitoring networks, and better forecast integration methods to extend the lead time and regional precision of El Niño forecasts. Quantifying climate impacts. Expanding the documentation of El Niño's global climatic, environmental, and socioeconomic footprints to better quantify its diverse impacts. Understanding past variations. Extracting more detailed paleoclimate El Niño reconstructions from sources like corals, lake sediments, and speleothems to contextualize modern observations. Attributing human influences. untangling natural and anthropogenic contributions to observe long-term changes in El Niño cycles through climate modeling and synthesis of real-world data. Projecting future changes. Reducing uncertainties around projections of El Niño behavior by developing Earth system models representing a wider range of interactions and feedbacks. Applying forecasts. Building forecast systems tailored for key sectors like health, agriculture, and disaster management to maximize societal benefits from El Niño prediction. While gaps remain, decades of intensive El Niño research have built a robust foundation for identifying its impacts and patterns. But this phenomenon still holds many secrets. Unlocking them remains imperative as its irregular dance will continue to shape human fortunes across an uncertain future. The far-reaching impacts of El Niño force us to expand meteorology into a system science, weaving connections across the oceans, atmosphere, land, ice sheets, ecosystems, and human societies. While a formidable endeavor, building this holistic understanding is key to anticipating, adapting to, and ultimately managing El Niño. Don't forget to like and subscribe to our channel so you don't miss new videos.